class we have discussed about the design philosophy. So there we learned that a very important factor in design is actually the decision making. Now not only the decision making, but several other relevant points are also been discussed in the last class. However, you understand that whenever we are going to design a machine or a machine element as it stands in our course, one has to take a decision. That's fine, that what should be the shape, size, etc., material, everything a designer has taken into consideration. But over and above, one should remember that ultimately one has to give a shape to his product. Now to give a shape to a product, it requires, what you understand is that, manufacturing. So we will discuss about the ideas of manufacturing in the context of design in this today's lecture, which has been given a name as Design and Manufacturing Lecture 2. In the case of design, when we want to make the final design, when we are considering, then one has to give a shape, as I told you, to the machine element, and for that you require to get some ideas of manufacturing, that as I have already told you. Now once again I am repeating the situation because this is very important. That means without manufacturing a shape cannot be given. So the first one we can think of in the manufacturing of a machine element is primarily its size. Now you understand, once we talk about size, say the shaft dia is 10 mm. That means you have to manufacture a shaft whose diameter is 10 millimeters. Now it is very difficult, irrespective of any manufacturing device, whatever may be its accuracy be, to get a shaft exactly of a 10 mm dimension. Hence, what people follow, that you mention some tolerances while designing a machine element. So that in one word is called limits and fits. We take up the idea of limits and fits in the manufacturing, before manufacturing and machine component, and let us discuss about that particular point. Let us have a look to the slide. First of all, we consider a situation which is something like this, that this one is a hole. Means if we consider this portion, this is the body where you have made a hole, and this is another object, solid object, we call it the shaft. What we understand, that any mating parts, just like an hole and the shaft, are being considered in this manner. That means what I mean to say, that any machine elements which is having mating parts are normally, while describing the limits and fits, are referred to as shaft and the hole. Shaft is a solid object which goes inside the hole, and this hole is also machined and the shaft is also machined. And as I told you that this machining, or in one word I am using the word machining, the machining implies at this moment a manufacturing, okay, while machining has got a typical implication that we will see later, but still here I am just loosely speaking, we are just talking about that it is being manufactured through machining. Well, while considering the dimensions of the shaft or the hole, that means you have machined a hole of this size and you have machined a shaft of this size. Now, here you can see one line in red color mentioning as 0 line. This is a 0 line has been referred to. What is the idea of this 0 line? Here you can see that onto the hole, of course, if we take a section, so this if we consider this one, then what we are talking about, if we take a section like this, then the one side of the hole, this line suppose, is in the same line of the shaft, or the bottom side of the shaft is coinciding exactly with the bottom side of the hole while we are viewing in the cross section. So, if we had made the shaft this particular point exactly touching to this line and this side of the hole exactly touching to this particular line, then what we would have told, that this, as I given as for the present example what I am just specifying, suppose this is 10 mm, okay, or shall I put it that this particular one, if we consider say some arbitrary value x mm, then the size of the hole when it comes over here is x mm and the shaft is also x mm. So, x mm shaft is going inside a x mm hole. That means the dimension, as we have referenced from this point, that means this point to this point, this length, what we called as an basic size. So, what we understand, the 0 line referred to be as the basic size with respect to a datum or respect to a reference line. So, ideally, suppose we do not consider any of the manufacturing tolerances, then we consider shaft is of x mm and hole is of x mm, thereby the drawing would have been something like that. This is the shaft size and this is the other one, would have been the simply the hole size. So, this is matching exactly in the same dimension, this hole is also x mm, shaft is x mm, which once again we consider to be the basic size. Now, you understand that just after looking through this drawing, that if we make both the hole and shaft exactly as the basic size, then it would pose difficulty in putting the two objects in this particular manner as two mating objects. The reasons being that you will always some inaccuracies in while manufacturing. Now, in this particular case, the shaft might be going inside loosely, it might be just a snug fit, or it could be a tight fit. Now, depending upon the situation, the x what the basic size, what has been referred to in the drawing, will have some changes of whatever magnitude be, but there will be some differences from the basic size. Normally what happens, when you give a preliminary design drawing, then we refer to the machine element dimensions in terms of basic sizes. However, one has to provide a manufacturing drawing to the manufacturer while your desired tolerance zones are to be specified. And this is, once again, let us have a look at to the figure and get some other nomenclatures normally used in design for giving to the final for giving it as a manufacturer's drawing. So, once we have understood the idea of the zero line and the basic size, then let us come down to some other definitions. The this blue colored zone over the ash colored, gray colored shaft, what you can understand is that this is the band of tolerance. Means if you are manufacturing, then the changes over the size could be anything within this particular zone. So, thereby you can see the maximum diameter of the shaft would have been this thing, and the minimum diameter of the shaft will be up to this much. So, anywhere we are keeping in between these zone and which is referred to as tolerance, what I have just uttered several times while talking about this particular manufacturing tolerances. So, this is what we talk about is the word known as tolerance. That means you keep your manufacturing of the product or the machine you are using for manufacturing in such a way that the shaft dimension will be somewhere within this zone. That means it will be lying somewhere within this zone. So, that is what we call the manufacturing tolerances. In the similar manner, what is happening that if you consider the hole, in this case of the hole, this particular zone, what we are considering is the tolerance, just like the way we have considered for the shaft. Now, again with reference to this particular zero line, what we are getting? We are getting two situations. One is that from the zero line, you are having the hole up to this much, one condition. Another one, from the zero line, you can go up to this portion. Okay, that means the upper limit, and that is this particular deviation from the basic size is called the upper deviation. So, this is the upper deviation. What we understand means, what we mean by upper deviation, this from the zero line, what is the maximum dimension of the hole which we expect, and the lower deviation, this lower deviation means this is the minimum diameter. So, you understand the diameter of the hole should be somewhere is a minimum diameter and it is going to be a maximum diameter. So, that just it is going opposite to the shaft. Okay, the maximum in this case is going up to the inside, and here also this much is the maximum in the shaft. So, if we try to find out the same idea, that means the upper deviation in case of the shaft, then this is the upper deviation and the other one will be the lower deviation. That means upper deviation refers to the word always, which gives you the maximum dimension, and lower deviation on the other hand gives you the idea of the minimum dimension. So, this is the lower deviation and upper deviation as I have told you. Now, all these deviations what has been referred to in this particular figure are always measured with respect to the 0 line or the basic size. Now, in this case there are several ideas one can think of. That means, if the shaft diameter is suppose 10 mm and we refer plus say plus x minus y. What it means? That means the shaft is having the nominal size or the basic size of 10 mm, whereas its dimension can increase by x mm in the upward direction, or it can be lowered by y mm in the downward direction. That means it can be 9 point something or it can be 10 point something. Now, this way if you are giving the tolerances both onto the upper side and the lower side, then it has got a name which is called bilateral. And in case you give the same dimension, once again 10 mm having minus side 0.0 and plus side say x, then it refers to an system. That means only in one side you are giving the tolerance, and that is sometimes referred to as unilateral. So, we understand that the tolerances can be of the two types, one is bilateral, another is unilateral. That means both sides you are giving tolerance, and or you are giving tolerance to the only one side. So, we come across certain definitions. The definitions are the basic size. Sometimes the basic size are the same as a nominal size. We understand in the similar manner. Then we understand the word tolerance, and then what we understand, there are deviation. Tolerance means the typical machine element, its bounds are known as the tolerance. However, we have also heard of a word called deviation. Now, this deviation means that from the basic size, how much the actual size of the machine element can deviate. That is what we call the deviation. Now, in this respect, one can talk about also another word which is called fundamental deviation. What is understood by the fundamental deviation? That means, if you are considering either of the upper deviation or the lower deviation from the 0 line, then either of these two can be referred to as the fundamental deviation. That means, in some cases you can consider the fundamental deviation with respect to the upper deviation, or sometimes also people can consider the fundamental deviation in terms of the lower deviation. I suppose that the figure, if we look into once again, then you understand what I mean to say. That means, here what I am just referring to it is that this is the line, this is the tolerance zone. So, this could be a fundamental deviation, means this is a fundamental deviation, or this is also sometimes also referred to as a fundamental deviation. So, these are the some useful notations or the useful words we normally think of when we consider the concept of the clearance, the tolerance, clearance and the deviations, etc., as referred to the manufacturing of an machine element. Now, in this case, you can see in the slide a word is written, it is called fit system. What is actually a fit system? Fit system means simply the English word how it fits, how a shirt fits on your body. Is it a loose fit, or it is a tight fit, or it is an over tight fit? Okay. So, normally people of in this particular difference, I can say like this: you will be finding out the shirts are normally a loose fit near the chest, but majority of the Indians we do have a tight fit at the stomach level. Well, so it also refers to the same thing when we talk about the mating machine elements. Again, we give the reference of the type of fits with respect to the shaft and the hole. Let us look into this particular aspect. In this case, you can see there is a hole as usual as it has been depicted in the earlier picture. So, this is the hole. So, in this case, the hole can have any dimension which starts from here and which ends over here, means anything starting from here to here up to this much. So, this as for our definition we consider this to be the tolerance zone, and this is what we are considering the minimum size, and this is the maximum size. In the similar manner, the shaft can have the maximum dimension and it can have a minimum dimension. In this case, we are referring all measurements from this size. Normally, what happens? There are two ways of representing these measurements. One is the hole basis, another is the shaft basis. What is the hole basis? That means we consider the dimension of the hole to be the to be the reference over which we make up the measurements, and shaft basis is the dimension of the shaft to be as usual being the basis of the measurement. But normally it is very popular thing to use an hole basis. The reason is that how do you make a hole? You will be, I think you from the preliminary workshop practice, you know, just by using a drill you can make a hole. However, if you make a shaft, you have to normally use a machine. So, making a drilled hole always have a more chances to have a fixed size compared to a shaft. So, thereby because of the manufacturing process involved in making hole being comparatively more fixed type in nature, hole bases are more commonly used compared to the shaft basis. So, here we consider a measurement which we will be considering as an hole basis. That means, the hole lines are the same and the shafts can have the different sizes. Okay. Well, in this particular case, what we are considering is that first of all, this is we call as an clearance fit. What is clearance fit? Clearance fit means the shaft will be moving inside the hole in a loose sense, means there will be a clearance inside the hole. How it is being seen? See, even if the shaft dimension comes out to be of this size, you can see that it is never touching the whole surface, where all the measurements being made from the same line, because the minimum diameter of the hole is always more than the maximum diameter of the shaft, and that is what we call as an clearance fit. Similarly, if we come down to the next one, there is also another fit which is called the transition fit. What is the transition fit? Means you can see that in the similar manner the shaft can have, this is the minimum dimension of the shaft and this is the minimum dimension of the hole. At this particular condition, you can see there is a clearance prevailing in between the hole and the shaft. So, there could be a clearance fit, as we have discussed for this particular case. In this same line, if we look into it very carefully, we can see that if the shaft dimension is this much and the hole dimension in this much, then there is an overlapping of the dimension, and this overlapping will be creating some sort of tightness in the fitting of the shaft inside the hole. So, we define the transition fit in such a way that it can create a clearance, as it was shown earlier, this is the clearance, or even it can create some overlapping fit. So, this is what we call as a transition fit. Normally, the press fit or the just a push fits are normally called the transition fits, where the clearance fits are sometimes referred to that where the shaft is freely moving inside the hole. The third in its kind is the interference fit. If we have a close observation, no matter what is the tolerance level, okay, in both the cases. The basic size of the shaft, as you can see, is ending over here. Just one second. The basic size of the shaft is here and the hole is somewhere here. Even if we go to the maximum size of the hole or minimum size of the shaft, there is always an overlapping in the basic sizes. So, that is what we call as an interference fit. This interference fit could be also from a pressure fit to a tight fit. This particular type of interference fit can be defined, where never a clearance fit will occur. So, these are the three types of fits we consider while we consider the design of the machine elements in terms of how a shaft is going inside the hole. Now, this is the idea. If you just look at the board, you can see we have drawn a schematic view of the another system, what is called the limit system. What is a limit system? Means what are the basically the tolerances or the fundamental deviations from the basic size. The limit system goes in this way. Say this is the basic size of the shaft, this is the basic size of the shaft, and this is the basic size of the hole. This is shaft and the hole. Whenever you cross, I think I should pick on the red color. Whenever we cross this 0 point, this is more than the basic size. When you go down, this is the less than the basic size, and that is what we understand as the fundamental deviation, what we have learned just before. Similarly, from the basic size, the hole can be larger or hole can be smaller. Now, here while considering the limit system, these are referred to as tolerance zones, where you can see that if we consider this limit system, these limit systems are denoted by the letters A to ZC, having all 25 divisions, where H is a special case we will come across. Similarly, for shaft we have the same A to ZC, but these are referred to in the smaller words. So, when we consider this feature, then you can see one thing, something like this. Say we consider the A, we consider this A zone. That means what is this idea? The A means that always the deviation from the basic size is this much, whereas the manufacturing tolerance is denoted by this much. Now, if we consider this is the manufacturing tolerance and this is what we are considering as the fundamental deviation. Now, just before considering this one, let us have a look to the limit system, what it refers. The standard tolerances are there, about 18 grades, which are referred to as IT01, which is referred to as IT01, IT0 and IT1 to IT16. So, 16 plus 2, 18 grades of standard tolerances are there. And as I told you, the fundamental deviations are 25 types, which are A to ZC as I have mentioned earlier for the holes, and small a to small zc for shafts. That means you can have a combination like this. Just you look at this figure. Suppose we have been talking about the A. For A, this is the standard fundamental deviation, okay. While we are considering A, this is A. When we are considering A, the fundamental deviation is this much, or the, however how you refer to. Let us refer to this is a fundamental deviation. As I told you, fundamental deviation is referred to with respect to the lower deviation or the upper deviation. Well, if this is the fundamental deviation, then this is the standard tolerance. If you are having IT, I would like to draw this figure once again, just for a clarity's sake. And this is the A. I have drawn in a smaller manner than earlier drawing. Reason is that this tolerance level, let us consider as say IT1. In the similar manner, if we take IT5 say, then this tolerance band increases. See, the look, fundamental deviation is A, but I am giving a more tolerance to the manufacturing. And if it is IT16, then the tolerance again increases. That means here one manufacturer can be very comfortable because he has got a wide tolerance. So this is the basic fundamental idea. Means you are having a fundamental deviation which is of the category A. However, for A, its tolerance in manufacturing could be IT1 suppose this much, IT10 suppose this much, IT16 suppose this much. Well, IT10 means from starting from here, I am sorry, not from here. Okay, this is an IT10 say. This is all schematic, and this IT01, IT0 and IT1 to IT16 etc. has got the standard values in microns, and for this you can refer to any standard manufacturing catalog or a design catalog. In both the cases you will get the standard tolerance values required for a manufacturing. Similarly, if you go for another fundamental deviation, say for B, C, so and so forth, you can express the fundamental, you can get an idea of the fundamental deviation in microns. Over and above that, you can have a tolerance grade for that fundamental deviation, which are denoted by 18 standards. So once again I go back to the earlier slide, which shows here that like A, you are having another one which is the H. The speciality of giving H, you can see the fundamental deviation for H is 0. That means sometimes this one is, that is one we call as an whole basis or something, where we do not have any deviation on the lower side from where the measurements are being made. And in the similar manner, you can have a shaft having a fundamental deviation 0. So this is an, if you are measuring the shaft deviation to be 0. So this is another way of the shaft basis. That means when we consider the whole basis, as you understand, that we told that all measurements are being made from the whole line. That means the whole lines are made to be the reference lines. Now here say this particular deviations, fundamental deviations 0 at the lower side, but whatever of the upper side, say this zone, if we had taken this much of block, this refers to say IT3. This much of block, say it refers to IT4, and this much say IT6, like that. That means what is meant to say that height of these blocks are basically referring to standard tolerances, whereas the later over here is designating you about the fundamental deviations. So, if we want to have a clearance fit, say for example, then can we not think of this zone? This is a zone where we can have the clearance fit, because you can see the basic size of the shaft is the size of the shaft, sorry, is lower than the basic size, and size of the hole is more than the basic size. So, there will be a very good clearance fit. However, in this manner, if you this particular zone, once again I think I should mention this particular zone of the H, if it is exactly like that, we sometimes use an word snug fit. Okay. So, this is the zone if we consider all the H zone. Similarly, if we go to the higher and higher along this line, you can see the fits are becoming the tight. That means, in this limit system, the fit you will be getting in the pair of machine elements will be of the nature of a tight fit, what we call as an this is interference fit, etc. Now, here of course, this is just an idea. I am just trying to say this is a clearance, snug, and the very tight fits. Normally, you know, people won't be referring to this zone. Very it's a very rare zone where you have this type of tight fits. Okay, this is mostly a very high hammering or pressurizing only can keep two machine elements, namely a shaft and hole, in a mating condition. So, this is what we understand by the limit system. So, what we have learned just up to this particular limit system, that means we know that a machined element cannot have an unique dimension. Here the word unique I mean to say is that you cannot have an one, you have to a dimension which should be little varying over nature. Varying means you have to specify a dimension having a zone, and that particular zone is what we call as an tolerance. And the deviation from the basic size, or the how big or how small from the basic size, we call as an deviation. As far as how a shaft getting inside a hole, if we want to clarify the condition, then we describe this by three types of fits. One is clearance, interference, and transitions. And lastly, we saw the limit system, where we define by typical word English words A to ZC, all capital for a whole system, and small a to small zc, all for the shaft system, to define what is a type of fundamental deviations normally adopted in a manufacturing of machine elements. And for that we do have this situation, which is like this. A limit system is defined by standard tolerances, which are of the 18 grades. Higher the grades means higher the tolerances, and fundamental deviations are of the 25 types, as I mentioned, A to ZC. Now, you understand that if you just going on machining on a lathe, then maybe this IT1, IT0 can be achieved for a very good machining systems, and a very standard one something like around 5, 6. However, larger sites like IT16 etc. Normally may occur in cases of some rough castings and other things. You can expect such situations. So, as for example, lastly, if you look at the board please, then you can see that I have written a word 50H6G5. what it refers to? It refers to its basic or the nominal size is 50 mm. H is the whole basis system, where the limit system using H means you do not have any lower deviation, fundamental deviation is 0 for the whole, and as is the whole basis, so it is written first, and 6 shows that in this zone you are using an it is 6 grade. Okay. So, that means this tolerance grade is 6th grade. Similarly, this G5 represents that you have used the G as the fundamental deviation, where you are using the 5 as the standard tolerance as for IT5. So, this gives you some idea, basic idea of how you dimension a machine element what you have designed when it is ready for what? Ready for manufacturing. Now, another important fact also comes is standardization, and the similar word is also called interchangeability. If you make a machine elements taking into these considerations, okay, that means you are giving an exact fundamental, exact limit and fit. Exact limit and fit, I think I mean to say that you mention that this machine element has been manufactured with this limits and fits, so that by any chance in a machine one of the machine element goes wrong, then you can utilize another machine element of the same dimensions having that much of the tolerance level. So, it gives you a very good interchangeability. Another important fact also comes in this line, what I just referred to as standardization, means you are making say rods, you are producing rods of different diameters, or you go to the market, you will be finding out you can purchase rods of 10 mm size, 20 mm size, 25 mm size, 30 mm size, like so and so forth. Many varieties or the many sizes are available in the market. Then what is the basis that which are the sizes one manufacturer should produce? Suppose if you are making a shaft, then what you do, you find out a dimension of the shaft, and then to manufacture that shaft you require a material, and then you go to the market and you can buy a material of your desired size. The desired size should be such that you will be having minimum amount of wastages. However, how do the manufacturer knows which size you require? If that is so, then they have to manufacture rods of infinite sizes, infinite steps. Many such sizes has to be stored in the market, but that is normally not done. So, what it is being done? Let us have a look. This particular idea is called the preferred numbers. What are the preferred numbers? Means it has been observed that if we make a size of any objects of various sizes, suppose our size is x, then was y, then as a z, like that, then all the sizes will have what? Will have a difference, something like that, which always follow a geometric progression. That means, in a GP series, if it is being made, then the sizes comes out to be quite logical. In the similar looking at this particular fact, these sizes do have a common ratio, just as we see in the GP series. To be more precise, what we understand that what should be that common ratio? Let us have a look to this particular one. When we talk about R5 series, now this word R has got a connotation. It is known as a Reynard series, okay, named after Reynard, okay. So this one what we get is something like this, that R5 means fifth root of 10, so which approximately value is 1.58. Now what you do is that you conveniently round it off. So what would be the sizes? 1, 1.6. What is, see, this one is rounded off to 1.6. Next you will be having 2.5, 4, so and so forth until and unless you reach the 10. Similarly, if it is R10, it is 10th root of 10, and this value comes out to be 1.26. 1, see here also it is rounded off in a convenient manner as 1.25, and you get a series like this. R20 refers to 1.12. Here you can see no rounding off as such has taken place. Similarly for the R40 series. That means these are called the preferred numbers, and all these are called as the basic series. Whereas if we multiply this by 10 or divide by 10 or 100, anything like that, then we get the series what we normally call as the word preferred series. So, I am sorry, this the spelling is preferred series, okay. So this is the preferred series we get. So that means this way one can think in the line that you manufacture these products by in such a way that you follow a definite series, so that you the designers know that I only get the sizes of this, so that if I design which requires something of say 1.1 and you are considering this series, and you know that you won't get anything like 1.1, so you have to buy 1.25, or you can search for this series if the product is being made as per this series. As I told, if the product is made, I can give you some of the examples. As for example, this R5, R10 and R20, this series are very common for the speed layout in machine tools. You know, machine tools runs at different speeds, so these are the speeds which can be as per the series R5, R10 or R20, but most common is this one. That means you can have 1000, 1215, 1600, 2500 like that. What I am doing, I am multiplying by an multiplication factor. You can have the powers of a tractor engine maybe 10, 16, 25, 40, something like this. You can have the feed in the machine tool as per say R20, which can be R20 or R40. These are used as the machine tool feed. Okay, you know machine tool feed, you have just done in your preliminary workshop classes. This particular things are made, I mean the machines or the diameters of the rod, what we say, that means ingots or the basic materials what will be used for machine element designs are made as per a standard which are governed by the preferred numbers. The next one we can think of that there are several one should have, although I am not going very details, I will be very quickly, I will just go through to give you the some ideas of the manufacturing processes. The manufacturing processes could be say the shaping, joining, machining, surface finishing and some non-conventional machining ideas. And over and above there is one called an heat treatment. What is this heat treatment? Whatever the machine element you manufacture either by all these methods can be ultimately can be going through an heat treatment process and going through an heat treatment process to increase its material properties. So, that is a heat treatment process. Now, here once you know this one, we just look into the shaping. What are the shaping? The shaping processes consists of say casting, forging, extruding, rolling. Casting, you know, that means you onto a mold you pour a molten metal and that gives you the shape of the machine. Forging means in the same way it could be cold forging, hot forging, you can just make the material hot or maybe cold also and then you put it into a shape by hammering in a machined way. Alright, that means you just by pressing the material either hot or cold you can get some shapes and of the machine elements. So, that machine elements are I mean made in a rapid way by say casting, forging, extruding is a very good example how you make out the pipes etc. Rolling, you know, sheet metals are being rolled. So, these are the shaping procedures. In the similar manner you can have the machining. You have gone through I suppose the turning, shaping, milling and drilling. These are the certain procedures you used in lathes and other machines, milling machines, shaping machines etc. And then you go for the surface finishing procedures which are mostly the buffing, honing, grinding, lapping and electroplating. Now, these are the surface finishing process, you will be learning more about these things. I am just giving you a just brief idea of the processes that are involved. And joining are the processes where you use the welding, riveting, brazing, screw joint, screws fashioning is also a joining procedure. And lastly, I go for a non-conventional procedures which you can see are given over here as ultrasonic machining, laser beam machining, electrochemical machining and chemical machining. There are several other varieties, you know, the ultrasonic machining utilizes mechanical energy, the laser beam machining utilizes a thermal energy. So, this is a thermal energy. This electrochemical machining uses an electrical energy and chemical machining uses of course a chemical energy. The ideas of non-conventional machining is coming out in a very big way and that we will learn later. So, I feel that you have got some ideas of the machining processes, how it is related to the design. So, we continue our discussions further on machine design in the next class. Thank you.